this tutorial, I want to talk about the Symbolics computing using Symbolics.jl package. So I open up the Julia repo and hit the right square bracket and type add symbolics and wait for the package to be installed. Symbolics and Sympy are both symbolic computation libraries, but they belong to different ecosystems and are designed with different programming paradigms and efficiency goals in mind. In short, Symbolics.jl is the package that wins because it's much faster than Sympy, and you can find the benchmarks and reports in the research papers, and also there are packages that are built on top of the Symbolics.jl, for example, modeling toolkit, which takes the symbolic model as input and transforms it into the language that is used by the Symbolics.jl. This way you might want to do, for example, manipulation of the symbolic model that you've got, and for example, simplifying it or changing it into something else. And Symbolics.jl uses in the backend a couple of other packages like metatheory.jl, symbolicutils.jl that I had recorded a video on it, and one of the developers asked me to actually stop recording videos about the backends of the packages, and that's reasonable because they might change and they might confuse the people who are beginners and want to use the package for the first time. And another great idea is integrating symbolics computing with numerical computation. What do I mean by that? For example, using symbolic manipulations at one stage and then converting the symbolic code into pure Julia functions and using them for numerical computations. And that's also possible. After the package has been installed, I open up the Julia repo again and type add latekify or latekify. That's for the package that converts the symbolic output to LaTeX code. After the installation is finished, we can simply check out the environment packages installed. I have installed Symbolics and latekify. I use the using keyword to import the Symbolics package and use the @variables macro to define two symbols, x and y. After defining variables as symbolic expressions can also be generated utilizing Julia expressions. For example, you can define z equal to x squared plus y. To make an array of symbolic expressions, we can simply make an array of symbolic expressions by defining the a equal to, and each element is a symbolic expression. For example, x squared plus y, 0, 2 times x, 0, 0, 2 times y, y squared plus x, and 0, 0. That's a 3 by 3 matrix. Now comes the reason we added the latekify or latekify package. Since I'm not using the Julia repo, A will not be shown with LaTeX equations. Symbolics.jl comes with latekify recipes, so it integrates well and works automatically. All I have to do is pass the array of symbolic expressions to the latekify function. However, this LaTeX code would be shown in the Pluto notebook, so if you're using the Pluto notebook, you won't have any problem. To create the sparse version of the matrix A, we just pass it to the sparse function using the sparse arrays package. We can thus use Julia functions as generators for sparse expressions. For instance, I have defined the function f and passed x, y, and z. Or we can build an array of variables and use it to trace the function. To create an array of variables, I just call the variables function in the symbolics package and pass the symbol and a range. For instance, here I have passed the 1 to 5, so I will get variables with indices. Another cool thing is representing derivatives lazily via operations just like any other function. Here I've defined a variable t, passed it to the differential, and got the operator. So if we want to write down the derivative of an expression, we can define an expression like z is equal to t plus t squared and pass the z to the differential operator. It's important to notice that we haven't computed anything yet. D is a lazy operator because it lets us symbolically represent the derivative of z with respect to t variable. If we want to expand the derivative operator, we use the expand underline derivatives function. And the variable that you are taking the derivative with respect to can be accessed by d.x. You can use the Jacobian function to compute the Jacobian of an array of expressions like x plus x times y, comma x squared plus y. Symbolics.jl interfaces with symbolic.utils.jl to allow for simplifying symbolic expressions, and this is done simply through the simplify command, and we pass the expressions to it and it simplifies it. For example, you can easily simplify polynomials. We can also use the substitute function to change values of an expression, but you have to notice that you have to pass a dictionary. And this can be used to interactively evaluate expressions without generating and compiling Julia functions. And you can reference the values via symbolics.value and pass the v variable. If you want to do symbolic computation on someone else's code, like in a macro, you may not want to do, for example, add variables and the name of the variable x, because you might want the name x to come from the user's code. For these cases, you can use the interpolation operator to interpolate the runtime value of x, that is, add variables and $x. An example of this is given in the documentation that I have provided for you in this tutorial. To generate new Julia code, we can simply convert the output to an expression by passing the expression to the symbolics.toexpr function. The other way around is also possible by pausing Julia expressions into symbolic expressions. For example, we have a couple of Julia expressions and we use the pause underline expr underline to underline symbolic and pass the expressions to it. We get the equations and we just try to get the left hand side and right hand side equations and pass it to the Jacobian function. Now I pass the xt and yt to the macro add variables. Then I define z as x plus y times t. Then I pass the dz to the expand derivatives to expand the derivatives. Since x and y are time dependent, they are not automatically eliminated from the expression. Thus, the dx and dy operations still exist in the expanded derivatives for correctness. You can also define unrestricted functions by passing g to the add variables macro and inside the parenthesis ... And also you can define z equal to gx plus gy. G is a variable that is a function of other variables. Anytime that we reference g, we have to utilize it as a function. One advantage of a fully Julia-based symbolic stack is that all primitives are implemented in Julia, making it effortlessly extendable directly from within the language. By default, new functions are traced back to these primitives, and symbolic expressions are built upon them. However, it's possible to expand the set of primitives by registering additional functions. For instance, let's register a custom function h. So when we use xy, it's a symbolic expression and does not expand. To use it with the differentiation system, we need to register its derivatives, and we do that like the following codes. So this way it works with the rest of the system. Note that at register underline symbolic only allows for scalar outputs. If full array functions are needed, then you have to check out the at register underline array underline symbolic for registering functions of symbolic arrays.